Scattering angles in center of mass and lab frames. The diagram on the left shows the center of mass reference frame where we have the angle theta sub cm, and the figure on the right shows the same scattering event occurring in lab frame, and the scattering there is theta sub lab. Our job is to be able to relate these two angles from the center of mass reference frame to the lab reference frame. Since we know that kinematics is best looked at in the center of mass reference frame, but the measurements are done typically in the lab reference frame. So let's start out by writing before the collision the momentum of the first particle in the center of mass is equal to the momentum of the second particle with a minus sign and is equal to just p. That's the initial momentum. The final momentum, p1 prime in the center of mass, is again equal to the opposite of the second particle center of mass prime and is given by p prime. Next, let's consider the lab frame p sub 1 lab, which is defined as mass of the first particle times the position of the first particle dot. Here we need the expressions that relate the coordinate of the first particle, r1, in terms of the position of the center of mass, plus m2 divided by m, total mass, times relative position r. Remember that capital M is simply m1 plus m2, and mu is m1 times m2 divided by capital M. Similarly, position of the second particle is given in terms of the center of mass r minus m1 divided by capital M times r. So we can find the velocity r2 dot in terms of the center of mass velocity, capital R dot, minus m1 over capital M relative coordinate dot, and that should be equal to 0 in the lab frame because the second particle is at rest before the collision. Thus, we find that the velocity of the center of mass for the lab frame is given by mass of the first particle divided by the total mass times relative coordinate r, or is given by the reduced mass divided by m2 times the relative position r, and it becomes momentum p divided by m2. We can rewrite the expression for the momentum p1 lab, and we get the following. P1 lab is now therefore given by m1 r1 dot. We take the expression for r1 and we substitute it into this expression to find m1 capital R dot plus reduced mass mu times relative position r dot, which becomes m1 divided by m2 times momentum p. Now we are using the expression of r dot equal to momentum p divided by m sub 2 plus p, which is given by this term. Let us introduce the ratio of masses m1 divided by m2 as equal to lambda, so that we can write for P1 lab to be equal to lambda P plus P. This is the momentum of the first particle in the lab frame before the collision. What is the momentum after the collision? It's easy to see that it's going to be P1 lab prime. The first term is going to stay the same because this is due to the motion of the center of mass. But the second term is now be given by P prime, the same P prime of the momentum in the center of mass after the collision. Remember that if the collision is elastic, the magnitude of the momentum before and after the scattering are the same. Now we can graphically represent this result. Given the momentum of the incoming particle, P, in the center of mass, and the momentum of the particle after the collision, P prime, the angle between them is given by theta in the center of mass. And remember that because the collision is elastic, we are looking at P prime being equal to P. Next, we are adding the component lambda times P so that the vector given by lambda P plus P is equal to P sub 1 lab, this expression here, and likewise this vector here is given by the momentum of the first particle in the lab frame after the collision, the primed values. P1 lab prime. And the angle between P1 lab prime and P is nothing other than theta sub lab. So by constructing this diagram, you can always figure out geometrically the connection between the angle of scattering theta in the center of mass and the angle of theta in the lab frame.